Here we're going to look at question 10 from section 2 of the ENGAA 2018 paper. In this question we're given the following diagram, which shows 3 springs connected in parallel to a rod, which is then connected to a single spring which is connected to a load of mass m. We're told that all of the springs in the diagram are identical and have the same spring constant K. Next, the question asks us, what is the elastic potential of this system? If you would like to have a go at doing this question yourself, then please pause the video now. Otherwise, let's have a go at it. So, as is often the case, perhaps the best thing to do with this question is to think about which equations we're going to have to use to help us solve it. So, since we've got springs, we're almost certainly going to have to use Hooke's law. It's kind of the fundamental equation which we use when we come to springs. So we'll see if we can use this at any point. Are there any other equations which you think we could use? Well, we've been told we have to find the elastic potential energy of the system. So we know with a single spring, that the elastic potential of that single spring is given by this equation here, where delta x is the extension of the spring and F is the force applied. But this might not initially seem too useful, since, as I just said, this is for a single spring. And as far as we can tell, we don't have an extension in the information we were given at all. But what we could do is we could substitute Hooke's law into this expression, and this would help eliminate the extension. So if we were to do that, then we get that the elastic potential energy of a single spring is equal to the force applied to the spring squared, divided by the spring constant of our spring. But this still might not seem too useful because we're talking about just one spring here. But can we think about any way in which we can convert this system into a single spring, or so that it acts as a single spring? Well, if we go onto a new page here and keep up our original diagram and this expression here for the elastic potential energy, then we know that with three springs in parallel, we can change them into being effectively just one spring. So there's a rule for this, which we can see in a moment. And now, in this scenario, we have 2 springs in series. And then similarly, there's also a rule where we can convert this into a single spring. So this system is actually equivalent to a single system, a simple system here with just a single spring. But in this single spring system, we still need a force to try and work out what the elastic potential energy is going to be. So can we think of what this force will be? Well, it's just going to be the weight of our mass, which is going to be given by the magnitude of our mass multiplied by the gravitational field strength, G. So we'll have an expression for force, and we're going to try and find this spring constant of our single spring. So, how are we going to find this single spring constant? Well, first let's try and find the spring constant of our parallel section of 3 springs, because once we've got that, then we're just going to have this effective spring here in series with a single spring, and then we can try and combine both of these into our single final spring. So what's the rule for converting 3 parallel springs into a single effective spring? Well, it's just that we add the 3 spring constants together. That's all it is. It's nice and simple. So in this case, the spring constant of our effective spring is just going to be 3K. Now, if you do have trouble remembering this rule, you can just think that 3 springs together are going to be stronger than a single spring. So if we're trying to find the effective spring constant of this single effective spring, then it's going to have to be greater than the spring constants are individually. So by just adding them together, we get a larger spring constant and therefore a stiffer spring. Now with this information, we can move on and try and find our final spring constant. So now we just have our 2 springs in series with one another. And can you remember what the rule is for finding the effective spring constant of 2 springs in series? Well, it's just given by this here. So the reciprocal of our final spring constant is equal to the reciprocals of our 2 spring constants added together. So just as before, where we were thinking of making a stiffer spring with springs in parallel, springs in series, you might imagine, are going to be a bit weaker, less stiff really. So this rule here gives a lower spring constant and a weaker spring. So that's sort of the way you can help remember which way this is around. But anyway, we can go ahead and find out what this is going to be. And so 1 over our final spring constant, Kt, is going to equal to 4 over 3K. which of course we can just flip to get that our final spring constant is just 3k over 4. So now we have our final spring constant and our weight, so we can plug these into our equation for the elastic potential energy and find our answer. Doing that, we get that our elastic potential energy is equal to a half of our weight, mg all squared, which is multiplied by 1 over our final spring constant, 4 over 3k. Which of course we can simplify by cancelling a 2 out of the 4 to get that our elastic potential energy is equal to 2 mg all squared divided by 3k, which is going to correspond to answer D given in the question.